At the outset, I would like to thank the organizer, especially Santosh sir, Bhagavati madam and Hemlata madam for giving me this opportunity to speak to you. Actually, we are planning to have sessions on hands-on exercises with SPSS, but before that Santosh sir said that you just have a session on basic and inferential statistics, so that it will be a recapitulation. You might be knowing all those things, but it will be a recapitulation before going to this hands-on exercise, so that hands-on exercise session you will not be asking if you have forgotten. I hope you have not forgotten, but if you have forgotten, you will not ask what is that, what is this. At least before that we are going to have the recapitulations of the basic concepts and these things, so that our hands-on sessions, 2 consecutive sessions in the afternoon will go smoothly. So, here some things will be repetitive, some things you will find more interesting, because we will give some examples with some real live data or with some international references, but the same basic statistics concepts. So, let us start with this without wasting any time. That what is the purpose of having this data? So, one nice statement given by an American best-selling author, because even he was associated with New York Times for quite some time, and then he is as a speaker, and he is fellow of Duke University, Dan Heath. He said that data are just summaries of thousands of stories. Tell a few of those stories to help make the data meaningful. So, when data are given, using that data you can build thousands of stories, at least tell few of them, but how to build that stories? And to getting a story out of the data, we have to analyze the data. You have to play with data to build a story. So, how to analyze the data? We have these statistical tools and techniques. Broadly, this can be divided into 2 parts. One is descriptive statistics, where we mostly talk about how to present the data as it is, how to read the data. There we present that organizing, summarizing and displaying of different data. And there are another component of statistics, which is inferential statistics. We try to draw some inferences based on the facts and figures we have in the data. So, here it's a very simple example, that a teacher arranges the scores obtained by his students in a graph. It's a descriptive statistics. But when another statement is given, a researcher may wish to find whether exposure to pollution reduces lifespan or not. Here you are trying to establish a causality between pollution and lifespan. So, you are drawing, you have a data of lifespan, you have a data for pollution. You are trying to establish a causality whether one causes other negatively or not. So, you are trying to draw some inferences based on the given statistics. So, second example is inferential statistics. So, here another example is there. Let us decide which component represent this descriptive statistics and which component represents this inferential statistics. A large sample of men aged 48 was studied for 18 years. For unmarried men, approximately 70% were alive at age 65. For married men, 90% were alive at age 65. So, if we take this descriptive part, that descriptive part statement provides that for unmarried men, approximately 70% were alive at age 65. For married men, 90% were alive at 65. So, what inference we can draw? A possible inference could be that being married is associated with a longer lifespan for men. I do not know whether you will agree with me or not, but using this data, this such type of inferences we can draw, that here the data represents like this. So, when we can play with data, we can do some analysis with data, but data are of different types. Very basic statistics, our undergraduate level statistics starts with the different types of data. The first one is qualitative data. There we say these are attributes. It's mostly that some examples are given that you cannot represent them with numbers. They are what major the student is studying, or their place of birth, or eye color. Different examples are given. Don't think I am good painter. All the pictures are taken from web only. Okay, I have not painted anything. Then quantitative variable, quantitative data. There are different data that can come based on measurement or counts, that age, weight or temperature. But again, this quantitative data are two types. One is continuous, that data, for example, measurement. Their measurement in inches or centimeter, or we can take example of weight, because it can go up to several of the decimal point, several of the fractions. And then we have in count data, numbers, how many students are there, how many teachers are there in this classroom. It cannot be 6.5 or 7.2, it has to be either 6 or 7. So, it is a discrete data. Here there is some examples are there. First is family. Presentation, then diagram presentation. Text on presentation, fantastic. There are some examples. The government has allocated a total of 2,440 crores to the various scientific departments. Out of which that 460 crore rupees is more. No, actually, this amount is more than the last year. And how much? That's 465 rupees. So you can present the data in very descriptive fashion. When such type of data are there, you just arrange the data in ascending or descending order. If you have arranged it ascending order, then these are the data of 40 students. How much score they got in the statistics test? 50 is the highest, but possibly it was out of 50. And you can draw some inferences from this, that is statistics class of 40 students, 3 students obtained the perfect score 50, 16 students got a score of 40 and above, while 3 got this 90 or below. So this data you can present in textual form. Fantastic. The second presentation is tabular format. You prepare a table, and there you will have a table title, then you will have column, and that column you will write that column heading, and then you will have different row, you will provide the row heading, and then you will provide the source of your data. If you have taken some, for example, in afternoon session we are going to have an exposure of NSSO data, national. You just provide the source that, or if you have done something with the data, you have not presented the data as it is, then author's computation using NSSO data like that. Some examples are there from my own paper that I had published a paper in EPW, Economic and Political Weekly. The title was "Why is Unemployment Higher Among the Educated?" There we tried to establish a relationship between unemployment rate and education status, whether this unemployment increases or decreases with the increase of the education level or not. So if you just see our last column, for 2011-12. That time the paper actually was published in 2018. That time that data was the latest data. So, and if you see the first column, different levels of education, and we can see with the increase of this level of education, this unemployment rate also increases. Quite surprising, and the paper talks about why is it happening, but provides some reason. But you can present, the picture is clear. Yes, unemployment expectation is that unemployment should come down with the increase of the level of education, because that is one of the purpose of having education, but this is not happening in Indian context for quite some time. It's not a recent phenomena. If you see from 1983, even the unemployment was increasing with the increase of the education level. So, you can present in that fashion. Again, in urban areas, this unemployment rate at the higher level of education is lower. That means educated people, at least there is better opportunities in urban areas compared to rural areas. But if we see this lower educated people, less that's not illiterate and literate up to primary education, their unemployment rate is lower in the rural areas. That means less educated people are finding better opportunities in the job market in rural areas compared to the urban areas, possibly due to some of the social initiative like NREG or something in the rural areas. So sometimes such type of stories you can read even based on this tabular presentation of the data. But fantastic presentation is their diagrammatic presentation of the data. And diagrammatic presentation sometimes can be so intense that it can even build a new theory. It can criticize the long existing theory. And some of the examples we have, but there are three types of diagrammatic presentations of the data: the geometric diagram, frequency diagram, and line diagram. We'll start with line diagram, but within geometric diagram there are bar diagram, pie diagram, and then frequency diagram also different types. We will come one by one. So let us have an example of line diagram. And this I have taken from a famous book published by Thomas Piketty, and this is now you know the name of Thomas Piketty, because in inequality debate his contribution is he is actually from Paris School of Economics, France, and he had contributed significantly in the inequality debate, publishing his book Capital in the 21st Century. And worldwide that has become famous. Now Piketty is one of the theme of research. He is no more a researcher, I believe. So you can see that how the existing trend of inequality, because if we see this trend up to this point 1942, that inequality first increases and then decreases. And exactly that was the argument of Kuznets-Stark. If we see that the relationship between the level of development and inequality first increase, and then with the level of development after a certain point of time inequality comes down. Actually that has happened. And if we take up to 1942, this is the inverted U-shaped graph. But Piketty has taken the trend after that also. And he has shown that yes, the trend is not as we are theorizing it, that it is always inverted U-shaped relationship with the level of development. Even it has shown that in recent times for the developing economies, this inequality is increasing, and that has even set a path for a kind of a serious debate across the world. And so you can see the significance of one single line diagram. It can criticize the long existing debate of this Kuznets-Stark, and it can even insist the new debate based on Piketty's paper. Now several research has started. And this is another example of line diagram. Actually, this was published by in a paper Martin Ravellian. Martin Ravellian is from Georgetown University, and he was associated with World Bank, and he is one of the significant contributor in inequality debate. And he explained this is the most powerful diagram in last decade in economics research, because this diagram was used when Donald Trump that was contesting for US presidential election. This diagram was used even the Brexit when Brexit happened. So he explained this is the most powerful diagram. Why? What this diagram talks about? You see the real income changes from 1980 to 2008. So the last 20 years, real income changes. And this is the percentage of global income distribution. And the argument is there, if you just arrange the population into different level of income, so possibly the developing countries, rich people of the developing countries come here that 60, 70 and 80, these kind of percentage. But the developed world starts, for example, US economy, their argument is that their population's income lies here, that 80, 90 and 100%. When there is a peak here, that means real income increases, those people are in 60th, 70th and 80th percentile. That means the rich people of developing countries were benefited due to this globalization according to them. And then here also the lower income people, because in rich countries their income did not grow significantly, but their rich people, the top 5% or top 2%, they are only benefited due to globalization. So there also inequality increases. So you can see the significance of presentation of data. How carefully, if you present it so carefully, how intense it can be. It can be even one of the means for even election campaign as well. So this diagram is so powerful according to this renowned economics. There is another diagram, but this is three. So far we have discussed how one line diagram explains a fact, but here we have presented three line diagrams. This is even taken from another well-known economist, François Bourguignon. He was former director of Paris School of Economics, and he has explained that why this inequality is increasing. He has bifurcated the inequality between countries and inequality within countries, and he has shown that yes, inequality between countries is coming down according to over the years, but inequality within a country across people within a country. So that's why inequality is still remains according to his data and his presentation. But my point is not to discuss inequality here. My point is here how the data can be presented, how data can be presented more meaningfully. So that is all about line diagram. Next is the bar diagram. Again, the relationship I have presented, that the relationship between education and this unemployment rate. The same thing you can present even with bar diagram. Bar diagram, you have equi-space and equi-width kind of this bar, and if you present like this, if this table you have to read, but looking at the bar diagram you can make out yes, it increases. Only exception, diploma and certificate course, their unemployment is much higher, but if we ignore that, at least it increases with the increase of the level of education. So that trend can be understood even with this simple bar diagram when we have only one category. If we have more than one category, here we have presented two categories. When I say that unemployment rate increases with the increase of education level, you may misunderstand me that means uneducated people are happy in the workplace. So this diagram shows that why these uneducated people are actually working. Uneducated people, yes, their unemployment rate is much lower, but why are they working? One account worker in the household enterprise, or work as a helper in the household enterprise, mostly unpaid family worker, or they are working as casual wage worker. So that means uneducated people's unemployment rate is lower than educated people's, but they are also in the low profile job, means casual job. Educated people sometimes do not want to join that low profile informal jobs. So that can be the possible reason, but this can be presented more than one category. Even you can bifurcate one bar diagram into different components. Here one bar diagram has been bifurcated that employment in agriculture by its different skill type, that high skill, medium high, low medium and low skill. If you bifurcate and you can see which component, what type of skill people represents, are engaged in which sector. So this type of kind of findings you can get from this bar diagram, component bar diagram. And we have one more diagrammatic presentation, that is pie diagram, and it's very significant. It's very clear. We, in one of our paper, structural change and economic dynamics, now its impact factor is more than 6. And what we have shown that if we just divide the total workforce into different skill level, that low skill, low medium skill, medium high and high skill, and then we can see that for Indian economy, which component we have more. And again, we have actually presented this diagram just to show that yes, our low skilled individuals are more, but that percentage there has come down from 49% to 37%. But all other, you can see there is an increase. That from this is, I cannot see the figure exactly here, 38 to 45. Even medium high there is an increase from 5.6 to 8, and for the high skill there is an increase from 6 to 6.2 to 9.7. Actually, our paper we had started with a debate of job polarization. Literature says that yes, there is a high demand for high skill and low skill job. There is not much scope for the medium skill people. But here we have shown for Indian economy, if we bifurcate this data by different, we had given a definition of skill, different types of skill, but we have shown yes, there is an uniform skill. Job polarization is not happening in that sense. So you can have even argument based on your this different pie diagrammatic presentation. There are few more diagrammatic presentations, that pictorial diagram, scattered diagram, statistical map. That pictorial diagram, different pictures are used. You know, scattered diagram mostly to represent the correlation coefficient. We use that scattered diagram. Represents the relationship for every dot, and then statistical maps are also used nowadays. GIS is very popular to show the significance of something in particular region or a location. Then we have one more diagram, that is frequency diagram. The frequency diagram, actually to understand frequency diagram, you have to understand frequency distribution. But frequency distribution has more significance in statistics. Actually, I believe statistics starts that from frequency distribution. What is frequency? Frequency is the number of occurrence of a particular element. For example, there are 3 values A, B, C. Qualitative data. You have got 3 grades A, B, C. How many people got A? The number of occurrence of that A. How many people got B? How many people got a C? So that number of occurrence represents the frequency. And once you plot that frequencies with over the values, then you will get the frequency distribution. How frequencies are distributed over the values? Values are arranged in ascending order. For example, your age I have taken, or your height, or your weight I have taken. In one side I am plotting your age, another side I am plotting the frequencies, and then I will get a frequency distribution. So frequency distribution can be simple frequency distribution. We will explain here what is simple frequency distribution. You have only one number, and for that one particular number you are trying to understand how many people, how many occurrence is there for particular number. But group frequency distribution, you have a range of values. There you have a group frequency distribution. We will come back to that point again. So here we have these are attributes. So grade of production in a factory, it ranges from A to E. So A, B, C, D, E. You know the tally marks how to give. If we count the first one is B, we will write a kind of standing line like B, then B, like that we will try to get a tally marks, and from that tally marks we will count that how many that this production got this grade A, how many the production got grade B. So we will write the frequency, and then individual frequency, if we divide by the total frequency, we will get relative frequency. And then we have two more concepts: cumulative frequency less than, cumulative frequency greater than. What is cumulative frequency? We will just, what is the difference between less than and greater than here? For this cumulative frequency less than, we will first get the frequency. For example, I have not counted here. For example, some 20 that is the frequency for A, and another 20 is the frequency for B. So here cumulative frequency will be 20. Here then it is 40. Then subsequently. But why do we need it? Why do we need it? Because looking at the figure itself, you can say how many production, how many people are just less than of this. Looking at the figure, you can say how many people are greater than. Here you can say how many people are greater less than of A. Here looking at this value, you can say how many people are greater than of this A. So you can represent, you can draw some inferences using that cumulative frequency here itself. We don't have that much time to do here step by step, but I assume you know. And then we have some data here for we have this 200 this unemployed individuals age data is there, and their names are registered in employment exchange. But the problem is, can we draw with this every age group, because there are so many 200 employees are there. So if we plot like this with each age, the table runs like this. One column is not sufficient. We have to add second column and third column. So sometimes it is very difficult to have that simple frequency distribution. So instead of having that simple frequency distribution, let us have a range. So we have seen that, okay, this working age group 15 to 59, we have divided into 15 to 19, 20 to 24, and then we have seen that how many people belong to that particular age group. We have any point? Oh, fantastic. So when this frequency is not for every number separately, we have clamped a number, few numbers, and prepared a range. It becomes a group frequency distribution. If we had presented it in single number separately, the previous table as we had shown, it is simple frequency distribution. So when we have this group frequency distribution, again that for group frequency distribution, we have this frequency for a big class, because now no more it is a simple value. So it's we will represent, we will call it a class, because it ranges from a lower limit to a higher limit. And then we want to find the middle value. The middle value of this class, we call it as a class mark. And then we will take the width of the class, and then we do all this exercise about this frequency density as well as that relative frequency calculation. Fantastic. So now you understood what is frequency distribution. Once we have frequency distribution, we can have these four types of diagram: histogram, frequency polygon, ogive, and frequency curve. This is this histogram. That it looks like bar diagram, but it is not exactly bar diagram. Bar diagram, it is space, but here we do not have any space because it is class boundaries. So it stops here at 20, 10 to 20, 20 to 30. So there is no gap here. So we can plot this histogram, but frequency got every class boundaries. And then we can have the middle value, that is class mark, and if we connect it, then we will get this exact frequency polygon. But if we just want to fit a smooth curve of this frequency polygon, we will get this frequency curve. Fantastic. And then we have two more concepts: ogive, less than ogive. We now know that cumulative frequency less than, we know that cumulative frequency greater than. And if we plot exactly, so cumulative frequency less than, we get this less than ogive. And if we plot this cumulative frequency greater than or more than, we will get this more than ogive. And exactly if we plot this, both the ogives and middle value intersection point provides us the median value. Fantastic. So we have now understood that how descriptively data can be presented. But frequency distribution presents something, it gives an impression about the distribution. But in addition to that, we need to know the nature of the data from a single value. How to come up with a single value? That first important measure is the central tendency. That the middle value. We want to take the average or the middle value, the central value of that distribution. So it gives some impression about the distribution, because so far we have presented the distribution. Now we are trying to understand the distribution based on one single value. So to understand even the central value, we have three different measures. You know in basic statistics, mean, median, and mode. Mean is the average of the data, it's simple average, and median is the middlemost value, and mode is the mostly upward value. The value has the largest number of frequencies. So if we plot it, this one I don't know whether you have studied statistics or not. How many of you have studied statistics earlier? All of you? At least 50%. At least 50%. Those who have studied statistics, they will not face any problem, but those who have not studied statistics, some of the notations can be new. But if you try to understand the notations in very logical manner, nothing. It's very simple, very logical. So here, we just have this. We will add all the values. For example, we have n number of values. If we have 100 individuals income, we will just have income. We will add all the income, then we will divide by 100. So n is the number of observation. And here, why have we used this sigma here? Those who have not studied statistics earlier, this is the notation of addition. So this is that sigma notation is the shorthand notation used to sum up a large number of terms, because when we have 100, it is very difficult to present. No? So in short form, we just use this capital C. Okay. So this is quite simple. So when we have this individual data, and they all are represented only once. For example, every individual's income we have taken. So their frequency is 1 by default here. If we take the income of every individual, so there is no frequency, that is ungrouped data. This is summation x by 1. But when we have the frequency, we have arranged with frequency, then we have to multiply with frequency, then summation f by xi divided by summation f. So summation fi is the total number of, f is frequency here. So summation of all frequencies is number of observation. So this is also number of observation, but we represent with summation f. Fantastic. So some empirical examples are there. So these are given that birth weight of few newborn babies, and if we find the arithmetic mean, we will just add all the weights and we will divide, because there are 10 the newborn babies weights are given, we will divide by 10, we will get. But here we have this number of male children, that 0, 1, 2, 3, 4, 5, and number of families are there. So now we are introducing from this one simple to this group data with frequencies. So here we can have this one, this x value is there, frequencies are there. We can multiply every 2x, and then if we divide with this total number of observations, are here 100. If we divide, then we will get it. So this is with frequencies we can get the average. Fantastic. So it has lots of advantages, this arithmetic. I mean, it is very easy to calculate. It is based on all the observations. It is easy to divide. It fulfills almost every criteria what we expect from central tendency. But it has a problem that it is influenced by extreme values. Extreme values sometimes in poverty measurement. For example, someone's, if we want to see the average earning, possibly this is well dressed up, possibly his income is much higher compared to others. And if we add it, that average income will go up. Average income will go up. So in that context, arithmetic mean may not be appropriate measure to represent the average picture. So here what we can do, another measure is their median. We can understand the middlemost value. If we take the middlemost value, then his income will not be affected to understand the median income. Even if his income is the few crore, but that will not affect to understand the median income. But here, if we have this, for example, how to get the median, we have to arrange the data first. If you forget arranging the data, you will not get the median value. So first criteria, you have to arrange the data in ascending or descending order. Most of the cases we arrange it in ascending order. Then we divide it by 2. So if you have, for example, 9 participants here. So how to get the middle value? 9 plus 1, 10 divided by 2. The fifth, if we arrange that fifth individual, the fifth person's income will represent the median value. But if we have 10 individuals, then whose income will be? So we have given, if it is even number, then you have to take this n by 2, that is n by 2 5, n by 2 plus 1, 5 plus 1 6. So fifth individual and sixth individual's income you have to add and you have to divide by 2. So you will get the median income from the even number as well. So this is an example that you can, this is only 7 individuals are there. So if you add 1, so fourth number will be your median. Numbers are given like this, and if we arrange like this, so 4 becomes our median value. So here we have given for even number example, and here if we 10 individuals are there, so it should be average of that fifth and sixth individual values. So you will get it. Now the problem is we have presented that class frequencies, class interval. So if we present that class interval, then how to get that data? So once we present the class interval, then also we can find the median, because if we take the lower value of this class interval, this L represents the lower class boundary, then width of the median class, then frequencies of that class containing median value, and then cumulative frequency. So you know it, so I am not going in depth each and everything, but when you have not very simple distribution, you have group frequency distribution with class interval, then also you can find the median here. Fantastic. But median, there is a problem that it does not capture that, does not cover all the observations. So sometimes median can be misleading also. But mode, another concept is mode, and mode is there the number of highest occurrence of a particular value. The value has the highest frequency will be the mode. But mode is very easy to understand, because from the frequency distribution table itself you will get it, the value of mode. But mode, the problem is mode is ill-defined. When I say ill-defined, you may not get mode every place. You see 3 examples we have given. That first example, you can see that every individuals we have one frequency. So which one is has the highest occurrence? We do not have any highest occurrence. One mode, here this is fantastic. We can get, okay, 4.9 is repeated 3 times, so all other values have frequency 1, but that particular value has frequency 3, so that value is the mode. So we have one example, no mode, another example, this is the ideal example we want it, but we may not get it that single mode. More than one mode is also there. For this distribution, you see, we have one, here one mode, 28 occurs twice, even 43 occurs twice. So this is more than one mode situation. So mode is ill-defined in that context. So here, we have given one more example here, but when you have this group data, again there is a formula to get this mode. There is a debate also how to get mode for unequal class interval. I will pass this slide. I am not going in depth into this discussion, because mostly we have this equal class interval. Sometimes it is difficult difficult to get it, but there is international level debates are there how to get it. This one because this one Indian Statistical Institute professor has answered that how different mechanisms can be followed. But there is some empirical relationship between mean, median, and mode. But when I say empirical relationship, it is empirical relationship. No theory is there behind of this relationship. So this mean minus mode equals to 3 into mean minus median. But this relationship exists only moderately. Distribution is like this. That bell-shaped curve, normal distribution, mean equals to median equals to mode. But if your distribution is like this, moderately skewed distribution like this or this, then only that is true. Otherwise, if your distribution is highly skewed, it is not true. So this is an empirical relationship with data it has come. There is no kind of theory, mass theory behind. But two more measures are there, very extremely useful measures. We have understood mean in terms of arithmetic mean, but we have geometric mean and we have harmonic mean. And this geometric mean, we can see the formula of geometric mean. It is the positive root of this product of observations. In arithmetic mean, we have added, we have taken summation, but here we are multiplying every observation. So these are for the with frequency and without frequency data. One simple examples are there. We have three figures 2, 3, and 6. If we multiply these three figures 36 and if we take this cube root of that 36, we will get this geometric mean. But why do we need geometric mean when we have understood all other measures of this central tendency? Because so far we have explained some of the obvious things, because this is quite important. Because in population growth, any growth measures, geometric mean is understood as the appropriate to understand even this growth. Here one example we have given that there are 100 oranges are there in the first year, second year it has become 180, then 210 and the next year 300. So growth rate of these oranges were like this 80%, 16.6% to 42.8%. And if we are so enthusiastic to take arithmetic mean of these three growth rates, if we add these three, or even if 1.8, 1.16 like that, if we add, it becomes 46.5. If we add it, but let us now multiply with 100 with this every year 46.50, then it is leading to 340, not 300 in the last year. So this type of this arithmetic mean for this growth rate may not be appropriate to represent the average figure. So what we have, we can get here that if we use the geometric mean of this figure, it comes exactly 44.22, and if we multiply all the 3 years, it becomes this 100 becomes this 300 in the last year. So what is the practical use of this geometric mean? One significant use that we all know Human Development Index. How many of you have heard about Human Development Index? Most of you have heard about Human Development Index. It represents the level of development of a region. So UNDP provides that comes up with this HDI value for every country, and they represent that figure shows the level of development of a country. Even within a country you can measure by the state, within a state you can measure by district. But how UNDP has reformulated their computation of this HDI from 2010, we can see they have now started using geometric mean instead of using this arithmetic mean to give equal importance to all the components. Do you have a marker here? Let us understand this with very simple example that why this has been used. For example, there are two significant components are there: health and education. For example, health value, health and education. Health value was 10 and education value was 20 in the first year. There is 1% reduction in the next year. 1% reduction on the next year of health. So 1% reduction. So if we take in the previous year, so the average is 10 plus 20 divided by 2, it is 15. Now, so here 1% reduction is there. 9 plus 20. So 29 divided by 2, it is 14.5. But if 1% reduction of education is there, then remains same, then it is 10 plus 18. So this is 28 divided by 2, it is 40. So what is the inference here? The value is higher. The product component value is higher. Even the reduction change rate is same, but it is giving more importance. You see, when there was 1% reduction in health component, it has come down 50 to 40.5. But when 1% reduction of education component, it has become 15 to 40. Because the value was higher. So it has given higher importance to the higher values. Had we taken this arithmetic. But in Human Development Index, they consider all the components as same. If there is a reduction in the health 1% and if there is a reduction of 1% in the education, the importance should be same. Now you see using geometry that the same formula that there is 10% reduction is there. So you take this one 9 into 20. So root over 9 into 20, that means it is root over 180. Isn't it? If we take geometric name, root over 180. 180 root over 180 value is 9.41 or something. Again 10 plus 18. Root over 10 into 18. That is root over 180. The value are same here and here. Whichever component it is, even for the higher values also, it does not give importance. Every component are equal. So UNDP has moved from this arithmetic mean to this geometric mean in Human Development Index computation. So likewise, there are different even other indices also is there. The retail price indices. Long time it has been given to measure the inflation of a country, and they use this geometric. But geometric mean also has certain advantages as we have explained, but let us try to understand the problem of this geometric mean. If some values are 0, for example, this value is 0, what will happen? If you multiply it with 0, it will become 0. And if the value is negative, again it will create some problem. So as long as the values are positive, you can go ahead with geometric mean, otherwise you can't. So that is the huge limitation of geometry. And then we have one more mean, that is harmonic mean. That is also another specific type of average. But if we take this formula, it is a little bit different because the use. Let us try to understand the use of this harmonic mean. One example I have given here to understand the speed. That suppose a car travels 100 miles from city A to city B at 100 miles per hour. But on the return journey, the weather is bad, so the car is forced to travel at a slower speed of 50 miles per hour. What is the average speed? So if someone tried to do it 100 plus 50 by 2, we have understood unitary method. If we go unitary method, exactly we will get harmonic mean. But average does not lead anything, because if we take the average speed, it becomes 75, and to cover this 200 miles at the speed of 75, it will take 2 hours 40 minutes, not 3 hours. So it is kind of misleading. So if we take the harmonic mean, it is like unitary method directly. You take the harmonic mean 1 by 100 and 1 by 50, you will get exactly 66.66. Fantastic. So we have understood different types of measures of this central value. But we have 3 different series here. So can you please tell me quickly what is the central value? Just take the simple arithmetic mean or median and tell me what is the this central value of all the 3 distributions. All the 3 distributions central value So central value speaks something about the middle or the average, but it is not sufficient to understand the distribution as such. So in addition to the central value, we have to understand even how other values are scattered, other values are dispersed from the central value to understand the distribution of the data. If we see this distribution, middle value is same, but the distributions are different. So the measure of this distribution is nothing but dispersion. So greater the variation among the different items of a series, the more will be the dispersion. So dispersion shows how the data is spread or scattered around the mean. So there are different definitions given by different statisticians, but meaning is same. So two types of dispersions are there. One is absolute, another is relative. As long as we are dealing with one observation, means one unit of measurement, for example, age of individuals in this class, or your age, something, as long as we are concentrating only with one category, this absolute measure is fantastic. But we want to compare between two groups. We want to compare between two groups when units are different. We want to compare, we will give some example. Their relative measure is most useful compared to the absolute. So in absolute measure, we have very simple measure of range, then quartile deviation, then mean deviation, then standard deviation. So range is nothing but the difference between the highest value and the lowest value. We have this data, and if we arrange it in ascending order, and if we take these differences, we will get it. But range can be misleading. How it is misleading? We have given two examples. That for this distribution, that range is 12 minus 7, 5. For this distribution is also 12 minus 7, 5. Although three values are there in the 12, it does not capture the distribution as such. Here you see how sensitive it is with the outlier. All values are same, only the last value, the highest value is 5 here. So the range is 5 minus 1, 4. Here the highest value is 120, 120 minus 100. Just due to the change of one value, the extreme value, the range is different. So range in that sense is not useful because it is affected with the extreme value. So another measure is their quartile deviation. It is half the difference between lower and upper quartile. In median, we have divided into two components, lower half and upper half. But in quartile deviation, we divide into four components: 25%, 50%, 75%, and then 100%. So this is the quartile deviation. That Q1 is n plus 1 by 4. Then as median, we got n plus 1 by 2 observation. Then 3 into n plus 1 by 4, we will get this quartile. So exactly we have with some data, if we have even number, exactly the way we got median, we will get this quartile deviation. Fantastic. But it has one huge importance. Even some of the well-known international papers or international level debate, you will see the use of this quartile deviation. There they say that high number summary. High number summary starts with the minimum value, then you will go to this your Q1, 25%, median Q2, Q3 and maximum value. It's called 5 number summary. And if you present this 5 number summary, you will get one box plot. Box whisker plot, plot, it will come in the next slide. We have given some examples of data. You get the Q1, you get the Q3, you have the minimum value 16, you have Q1, you have median, you have Q3, you have maximum value. So let us plot this one. If you plot this one, you will get such type of plot. You will get such type of plot. And these plots are known as box whisker plot. Actually in short form, box plot. Box plot is very useful to understand the distribution across different quartile, and we can see that this box represents our interquartile range. What is interquartile range? It is the difference between Q1 to Q3. and the median, this one, it divides by Q2, that is nothing but median. So interquartile range is given with the box. Two whiskers are there, two tails are there. These two tails says that from 25% to the lowest level. And we can see the distribution of this lowest here. So much. The lowest 25% belongs within this distribution. But for this one, you can see lowest 25% is very concentrated, very much concentrated in this 25%. So it is not that kind of deviated for the whole people. But if we say it is that from 25% income, the person is in this Q1, his income is like this. It is much higher than this the lowest income. Even the highest also, we can see the richest income. From the 17th position the person is there. We can understand even the distribution here. So this is very useful to understand the distribution and this inequality. So most of the times temperature is presented in weather report with this quartile deviation. So quartile deviation also does not incorporate all the values. So it has one limitation that it does not include all the observations in their estimation. But we have two measures which incorporates all the estimations in their measurement. One is mean deviation, another is standard deviation. But mean deviation, this is the formula that what is mean deviation? We have for example 5 values. 1, 2, 3, 4, 5. What is the mean value here? 3. If we take the differences, that 1 minus 3 plus 2 minus 3 plus 3 minus 3 plus 4 minus 3 plus 5 minus 3. We can take these differences from the mean value, and then if we divide by the number of observations, we will get it. But here the problem is that they just ignore the sign. They ignore the sign. They take the differences of this absolute. Why do they ignore the sign? Because we know the mean deviation from the mean, summation of the deviation from the mean will be 0. So just to avoid that, they just ignore the sign, and if we take, it will be 0. But if we take the absolute, ignoring the sign, it will not be minus 2. It will be plus 2 only, because we are ignoring the sign. So this is mean deviation, but there is a debate. This is one of the example of how to compute mean deviation, but the issue is that it ignores the sign, so it is not very much scientific or mathematical. So standard deviation, there are some papers I have even quoted here. You can even read, because some statisticians argue that yes, mean deviation is still better than the standard deviation, but hugely statistics we have in subsequent part of the statistics we rely mostly on standard deviation, not on the mean deviation. So here you can see that instead of taking the absolute differences, what standard deviation does, they take the square and then the root. So once we take the square, then even if it is minus 2, the square becomes 4. So we just take the square instead of ignoring the sign, because it goes with this scientific or the mathematical reason. So if when we have this without frequency data, we get this mean this standard deviation, and little bit formulation we can come up with this figure, and variance is nothing but the square of the standard deviation. Even standard deviation can be computed when we have this class data with different class intervals, then also standard deviation can be made. But we said that we have another measure. In addition to this absolute measure, we have relative measure. And relative measures are that coefficient of variation, because if we take the standard deviation in the numerator, we divide by mean in the denominator, and we get this relative measure. And relative measures are very useful here. You can see here, we have given an example that mean rate of return is there. 12.2% here, 12.2%, and then standard deviations are there. Now take a look. If mean is same, standard deviation, even if we divide standard deviation by mean, meaning remains same. No? So, as long as mean is same, we can compare the standard deviation between two different distributions. But if mean is so different, here we have given an example that mean value of this closing price here 2 and here you can see this mean value is so different here. So when mean values are different for these two distribution, we have to go ahead with this relative measure of this distribution. You can edit this example because I am running little fast. But if those who have not studied statistics, that just you see this one, that two different investment with the same mean rate of return considered. Now the owners are considering purchasing share of stock A and share stock B. Both listed on the New York Stock Exchange. From the closing price of both stock over the last several months, the standard deviations were found to be considerably different. With for stock A it is $2 and stock B it is $8. See, $2 and $8, it looks like okay, $8 is very high if we go ahead with the standard deviation. $8 standard deviation is high. So looking at the standard deviation, we will choose okay, no. First one is lower standard deviation, low risk, low variation. So let us go ahead. But actually this is high because the value itself is high. All the values are there. That's why it is high. Once we take this one, once we divide the standard deviation by mean and multiply with the risk is only variation is relative variation is 10%. And here the value is mean value was 2, and if we standard deviation is 2, mean value is 4, and if we multiply with 100, it becomes 50%. Looking only at the standard deviation, sometimes it will be misleading. Another example we have given is a comparison between wage and electricity. Unit of measurement itself is different. How will we take the standard deviation? One is measured in units, another is measured in something else. So here, so the use of coefficient of variation of the relative measure is that when absolute measures cannot be used for comparing dispersion of two or more distribution within different units, the coefficient of variation is a unitary number and may be applied for this. And another condition is that while mean of the distribution are widely different, although given the same unit, a relative measure will be more logical than the absolute measure of distribution. So you understood at least the basic statistics. So we will. Can I take another 5 minutes, ma'am? Fantastic. So far we have discussed only one distribution, one particular categories or observations. But when we have two sets of values, then how to compare, how to come up with their associations. So two measures are there. One is correlation, another is regression. Correlation, it represents the association between two values. It does not confirm any causality or anything. Correlation does not mean causation. It just shows how both the values are moving. They may move in the same direction, they may move in the opposite direction, but one does not cause out. They may cause, but correlation coefficient does not confirm. Okay. Even to get that conformity about the causation, whether one is really affecting the other, we have to go for regression analysis. That's the basic difference between correlation and regression. So the correlation provides the degree of association between two or more variables. So here there are different types of correlation. Positive correlation, if both are moving in the same direction. If both are moving in the opposite direction, there will be negative correlation. We have given an example that price and demand of a commodity. If price increases, demand will come down. If price increases, will you buy? You may lie. It does depends on so many other things, but in logical sense, it's yes, when all other things are equal. So price and demand, it can be negatively related, but sometimes you can see this height and weight or the price and supply of a commodity, they are positively correlated. But there are different types of correlation also, because simple correlation can be there if there are only two variables. Height, weight you want to measure, but then you have introduced one more category within that. Whether their parents earning matters for height and weight or not, with parents earning. So one more category you have introduced. When you have introduced one more category or more than two variables, simple correlation, you have to go for either partial correlation coefficient or multiple correlation coefficient. Partial correlation coefficient, just now you said that keeping other things constant. Association between two variables, keeping the third one constant. If we consider that, we will get the partial correlation coefficient. If we consider all others are varying at the same time, we have to go for multiple correlation coefficient. So correlation coefficient, so there are different presentation of correlation coefficient. We can measure graphically and we can measure algebraically. Graphically, we just get this scatter diagram, how these both are moving. It may move in the positive direction, very perfectly positive correlation. It may have positive correlation still, but it is low degree positive correlation. It can be there can be no correlation. So different types of the relation we can association we can identify just plotting the scatter diagram. But it does not provide the amount of that exact correlation coefficient. So for that, we have to go for this correlation measures of this correlation coefficient, and that correlation coefficient measure is that covariance of two variables x and y divided by sigma x standard deviation x into standard deviation y. So I am not going in depth into this thing. So once we get this two data, and if you just find this one, and then you can come up with easily this correlation coefficient measurement. So interpretation, it is highly dependent on the covariance, because covariance is in the numerator. If covariance is positive, then the relationship is positive. Covariance is negative, relationship is negative. If covariance is 0, then the relationship will be 0. But it ranges between this -1 to +1. But sometimes you may not get this exact value, the roll number of the rank of the students, or some cases you need to rank them. When you don't have that continuous variable, that Pearson's correlation coefficient is not an absolute measure. In that case, you have to go for this rank correlation coefficient. I have given one example of the rank correlation coefficient is the Spearman's rank correlation coefficient. You have the data, but you have ranked it first, Rx and Ry. Then you take the difference and then you go ahead with this measurement. So you will get this rank correlation coefficient. This is not that correlation coefficient of continuous variable. What is that partial correlation coefficient? Here you have more than two variables. You are measuring a relationship between 1 and 2, keeping the third one constant. The same with 1 and 3, keeping the second one constant. Like that, this is the formula. But first you have to estimate what is R12, R13, R23. R12 is the simple correlation coefficient between 1 and 2, first variable and second variable. R13 is the simple correlation coefficient between first variable and third variable. So to get the partial correlation coefficient, first you have to estimate the simple correlation coefficient between two variables, and then using that you can estimate the partial correlation coefficient. Because partial correlation coefficient is very effective. We can understand this one. We have three data: achievement, academic achievement, anxiety, and intelligence. And there we can plot this one. That the relationship between academic achievement and intelligence. But anxiety also matters. In exam hall, you are so tense. You are intelligent, but you are so tense, you could not perform. Anxiety also matters. So once you control for anxiety, then you will get the correlation coefficient between this. So how to control for the other variable? You will get this one, this RA dot B. So then even you can test whether this is, you will get a correlation but whether that is statistically significant or not. So you have to compare that calculated value with the critical value. If it is lower than the critical value, you accept the null hypothesis. That is partial correlation. There is no correlation coefficient, no statistically significant correlation coefficient. If your calculated value is greater than the critical value, then there is statistically significant partial correlation coefficient. So you have to compare between calculated value and the critical value. So even if there is more than 3 variables, if there are 4 variables also, you can estimate partial correlation coefficient. There are number of variables, n number of variables. Just using the same type of formulation, you can estimate this partial correlation coefficient. Then multiple correlation coefficient, again the formula is given. You can estimate multiple correlation coefficient as well. But now we have understood the association between two variables, how they move, whether they move together in the same direction, or if one moves in one direction, another moves in opposite direction or not. But whether one causes for the other or not, that has to be confirmed through the regression analysis. In regression analysis, then we have one dependent variable, one independent variable. As long as you have one independent variable, it is simple regression model. But in reality, as I said, demand depends on so many other things. To establish the causality, you have to introduce other variables as well. So when you introduce all other explanatory variables, independent variables more than one, it becomes multiple regression analysis. So here this is one simple formula that your y depends on x, and it has origin and it has some error value. I am not going to discuss in depth here, but in our practical class we will take one regression result and we will try to interpret, we will try to understand how regression results are interpreted. But to establish the causality, you have to have this regression analysis. I would like to stop here for this session. Then I know I was quick and it was a repetition for some of you, but I believe this was recapitulation also, so that we will have our smooth hands-on exercise session. Thanks.